Greetings, everyone. Welcome back to Calculus 1. Now it's time to start putting our money where our mouth is, right? Especially with our calculus calculations. We're going to start an entire chapter here of applications of derivatives. We've talked all about the methods of finding a derivative, and every now and then we've snuck in a little bit of how to use a derivative with graphs and tangent lines, and we talked a little bit about velocities and rates of change, but now it's time to hit some of the actual application topics here. The first one will be related rates. And the idea of a related rate is if you can find some sort of relationship between two measurable quantities, especially between one that's easy to measure versus one that's more difficult to measure, then related rates will give you a deeper connection besides just being able to calculate stationary measurements. So what you need is some sort of equation that relates either one variable to another or one variable to several others or whatever. And when we say equation that relates things, what am I really saying? A formula, right? Any kind of formula that relates one quantity that you would calculate versus other things that you measure first and then input is the kind of equation that we're looking for here. Okay? So what you're going to have is to set up the formula from some sort of situation, but instead of just plugging in numbers, what we'll first do is do some implicit derivatives, and that will cause some rates to come out in a new formula. Okay? Now, of course, when I say implicit derivative, it doesn't necessarily mean moving things around in the equation. It doesn't necessarily mean picking d over dx and involving y. Most of the time, the implicit derivation involves some sort of variable that doesn't appear in the formula itself. And so it basically treats everything as a function of something else. A common thing is time, right? Time doesn't always appear in a lot of our formulas, but it's used to measure things that go into formulas all the time. For example, if you have some sort of distance calculation and you want to know the distance at several different moments in time, the distance calculations themselves may not involve time, but if you want to let the distance calculations move, well, then you have some sort of rate as the distance is changing over time. You have velocities. Okay? So here's a couple of quick examples, some things that are already set up so that you can just get the basic idea. And then we'll move on to working some of the word problems that go along with this. All right, so right here, I've got a right triangle, and I've let the legs be x and y, two variable quantities. Since this is a right triangle, I can create a relationship between y and x directly using Pythagorean theorem. So here, 5 squared is equal to y squared plus x squared. That's an equation that relates y and x. So if I were to change x a little bit, it would cause y to change a little bit, right? In other words, if I pulled x shorter, y would have to get taller because the 5 is constant. So they would have to constantly obey this relationship. Okay, so if I were to let x change over time, like let's say let x move closer to the y line slowly over time, then I would actually be measuring a rate of change in x, and I would call that rate of change dx dt. But then that would cause a change in y. Okay? So here's the thing. Sometimes these relationships are all about how does changing one thing affect another one. And sometimes these things are all about if I change something I can measure, how does that affect something that's difficult for me to measure? Okay? So this first one, it's the first thing I said. I just want to know how changing one of these things would affect a change in the other one. I could easily measure the lengths of x and y independently, okay? But I want to know how changing one affects the other, so that I can see what kind of relationship they have, right? So what I do is an implicit derivative here, d over dt. Notice t is not anywhere in the equation, but that's okay. I can still do a derivative with respect to it if I label x and y generically functions of t. In other words, I'm stating that there's a possibility that changing this variable t would affect x and y. Even though t doesn't appear in the equation, I could have it somewhere else defined as, okay, x depends on t this way, y depends on t that way. Or, like I said before, just think of t like time. Obviously, if I'm going to move x, I'm changing it over time. So, the derivative with respect to time, if you want to think of it that way, right? It doesn't have to be. T can be just some generic variable. But basically what's happening is I'll just treat y and x like they're functions of t. So I would have a chain rule on both of them. The 2y derivative here from the y squared is the outside, and then times dy dt because of the chain rule, plus, again, derivative of x squared is 2x, and then times dx dt because of the chain rule. Of course, the derivative of a number is 0. And then this gives me a different relationship between y and x. It gives me a relationship that involves them changing over some other variable t. If you want to think of it as time, then this could be the velocity, or well, rather the speed, not the velocity, but this would be the speed that y is changing, and dx dt would be the speed at which x is changing, right? And then I could even solve for one of them. For example, I could get dy dt by itself, and then I would have a calculation that I could plug values in for to compute dy dt. So in other words, if I knew how fast x was changing, I could plug in a value for dx dt. That would be just a rate, right? And then I could plug in a position for x and y that particular moment is occurring, and then I would get how fast y is changing, the dy dt calculation, okay? So the whole idea is I have this equation, I can do some sort of implicit derivative, and then I can relate the rates between x and y, okay? Here's another example. The shape called an annulus is two concentric circles, but it's the area between them, okay? So if I'm measuring the area between these two circles, I'm measuring the area of an annulus. And what I really need is just the knowledge that they are concentric. In other words, they have the same center. And I need the radius of the large circle and the radius of the small circle. And the area is pi times the difference of them independently squared. This should sort of make sense to you because all I'm really doing is taking the area of the big circle and subtracting the area of the smaller circle. Pi big R squared minus pi little r squared, and I just factored the pi out. Okay? So this is a formula that relates the area to these two measured radii from the two different circles. The radii, very easy to measure, right? There's two lengths that I could put some sort of tape measure or ruler if it was on the ground or whatever, or if it's on the board, right? I could use a ruler. But the area is not so easy to measure, right? It's a measurement in square units, and I would have to find something that is a square unit and put it in there and count them, or find a way to grid it out, and then you'd still have to find a way to compute the partial pieces. Area is not as easy to just flat out measure. Usually areas have to be computed, right? So in this case, I would want to know the change in area if I were to change one of these two radii, like if I were to shrink the inner circle or if I were to grow the outer circle, right? What would the change in area expected to be? Okay? So I again have this relationship, and I take a derivative with respect to t. And again, you can think of t as time, but it doesn't have to be. It can be just some other measurement that you're doing outside of this that controls the rate of change. Okay? Time is an easy way for us to conceptualize that, but it doesn't have to be. It could be something else controlling the change. Okay? But t is the variable that I'm doing my derivative with here, just to be generic. So over here, easy derivative, just dA dt, right? Because it's derivative of capital A. So dA dt is the measurement of the change in the area as this variable t changes, right? So whatever t is controlling the change, as it changes, dA dt is the measurement of the rate of the area change. Okay? And then over here, I took my derivative, right? The derivative of the r squared, again, is just 2r dr dt with capital R. And then I multiplied pi into each piece. And then here, again, the derivative of the little r squared is 2 little r, and then times dr dt. Basically, I'm just treating every variable like an implicit derivative, and I'll always get times d whatever that variable is, dt, in the derivative equation here. Okay? Interesting thing that you might notice, though, 2 pi r is the measurement of the circumference of the bigger circle here, and then 2 pi little r is the measurement of the circumference of the little circle, times the rate. That should sort of make a little bit of sense, right? If I were going to increase the area of the larger circle by pulling the radius outward like that, it would be like increasing it by a larger circle, right? The circumference keeps getting bigger, so it's like laying on more layers of circles. So in other words, I increase by changing a circumference, right? Getting the next circle larger up, times however fast that's happening, right? Would be the way that's increasing. The same thing for the other one, right? If I were to decrease them. One other thing to remember is that these changes, like d big R dt or dy dt right here, those values can be negative or positive. So you need to pay attention to the wording in these things. If I say x is increasing, right? So in other words, x is growing, I would let dx dt be positive. But earlier, remember I was saying, what if I brought x closer to the y line, right? Then technically x is decreasing in that situation, and you would actually put a negative number in for dx dt. It would be negative whatever the amount it's decreasing is. So keep in mind when you're doing these things that your derivative values, your rate values, can be negative or positive. First example. Let's go old school with this, with one of the most traditional types of problems that people use with related rates all the time. The stereotypical falling sliding ladder. So we have a 21-foot ladder that's just leaning up on the side of a wall. And I guess somebody, thought it'd be cute to put the, ladder on gravel or grease on the floor, maybe, as a prank, or who knows, right? The point is, the bottom of the ladder starts to slide out from under it. And in doing so, since the ladder is rigid, right, if the bottom slips out, the top is going to slip down. We're assuming that, someone's weight is keeping the ladder pushed up against the wall. So the ladder is going to stay attached to the wall and basically scrape its way down as the ladder, just does this. So here's the situation. If the bottom is constantly moving at 5 feet per second away from the wall, then how fast is the top of the ladder dropping, right? Excluding all the other factors. How fast is the top dropping when they're actually at 16 feet high? So imagine, the 21-foot ladder is reaching something higher than 16 feet, like maybe they're at 18 feet or something, and then it starts falling. And then right at the moment that the ladder hits a height of 16 feet, right? They want to know at that moment, how fast is it going? Because you may not have realized this, even though the bottom is a constant rate, the falling doesn't have to be at the same rate at every moment. And that's because it's not a linear relationship between the two, right? As I'm about to show you. So, what we have is the ladder leaning up against the wall here at any given moment, right? As the moments go by, the ladder would be in different positions, but this is a generic representation of any given moment. I know not the best drawn ladder in the world. I was trying to give it some perspective. Anyway, at any given moment, I have this kind of relationship between y and x. The building is supposed to be level with the ground, level-ish, close enough to 90 degrees to count for what we're doing here. Okay, so then, according to Pythagorean theorem, I have 21 squared is equal to y squared plus x squared, right? So 21 squared is 441. So let's go ahead and just write that. 441. So I will need to use this for some of my information, okay? But let's get the related rate equation first. This is the relationship equation. Now I need the related rates equation. So I'm going to do a derivative with respect to t of both sides. Okay? That gives me 0 is equal to 2y times dy dt plus 2x times dx dt. And before we get too far in this, by the way, you'll notice I drew a picture, but it is good to have something stating what each thing is, okay? So if you're trying to write this up in an organized fashion, or if you need to present this to someone, you may actually want to write out x represents the distance that the ladder of the bottom of the ladder is from the wall, y represents the distance that the top of the ladder is from the ground, so on and so on, so that these rates right here actually have more meaning to them, right? So then dx dt is going to represent the rate at which the bottom of the ladder is moving away from the wall. dy dt is going to represent the rate at which the top of the ladder is approaching the ground at any given moment. Okay? And also let me comment, this isn't just normal, just finding speeds over some periods of time. Don't forget that derivatives are measuring instantaneous rates. So these dx dt's and dy dt's can be something different at any given different moment, which is why I was particular by putting constantly on this one. So dx dt is constantly 5 feet per second. Okay? Now, is it positive or negative? That's going to be the next question. Before we get to any of that, though, remember we're solving for the rate at which the top is falling. So I want dy dt isolated. I'm going to subtract the 2y over with the dy dt, like so. Then I'm going to divide both sides by negative 2y. So I have dy dt is equal to negative x divided by y times dx dt. And, the 2's just eliminated there. Okay? So I have a related rate equation here. I'm relating the rate of y changing to the rate of x changing. And it has this extra piece, x over y. And that's the part I wanted to comment on from earlier. Even though the x rate is constant, the y rate is not going to be, because the x and y coordinates are changing. So as those change, they multiply and divide into this calculation, and that's going to make my dy over dt rate different at different moments. So it does matter which moment we're talking about, which is why the extra information over here is important. Okay? So we have to comment now, before I can finish the problem, the moment that x equals 16 feet. Oh, I'm sorry, not x equals 16. Y equals 16. I should have been more careful. A ladder is 16 feet high off the ground. That's the y coordinate. The moment that y equals 16 feet. Okay? So that's like a freeze frame. The ladder's falling, freeze. At the moment, right? We're going to talk about this singular moment. Y is 16 feet off the ground. Okay? Well, in that moment, 441 is going to equal to 16 squared plus x squared. 16 squared is 256, and I'm going to subtract it from both sides. Okay? So then I'm going to get 185 is equal to x squared. Square root of 185 is then x. Of course, I'm only going to pick the positive, not the plus and minus, because x is a distance. So what I have here is the x and y values at that moment. These are not rates. These are measurements of the distances at that frozen moment in time when this is occurring. Okay? So x is the square root of 185. Let's see, that's 5 times 37, so you can't reduce it. Square root of 185 should be something in the teens. 13.6. Okay? So it's around 13.6 feet away from the wall. Well, now I have a y value, I have an x value, and I still have my rate of change of x as being constantly done at every moment. So I can plug those three values in, right? dy over dt is then equal to negative square root of 185 divided by 16 times positive 5. I want you to notice that I'm putting a positive 5 in because dx dt says that it's sliding away. The x distance is increasing. Be very careful plugging in these rates. Positive and negative makes a difference. Okay? Let's number crunch this up real quick. Square root of 185 divided by 16 and then times 5. We have 4.25, but it's negative, right? So dy dt is approximately negative 4.25. And I'll go ahead and write the units in feet per second. So that's how fast at that one moment the top of the ladder is falling. And notice the rate did come out negative. The height is decreasing at that moment. Okay? Next example. Let's take a look at a balloon that's thought to be spherical. Well, of course, they're not always perfectly spherical, but we're just going to assume that it's mostly spherical. Okay? So what we have is the balloon set up in a rig, and we're allowing the air to release once I let go of the spigot, basically, right? So the air is being released, and it's flowing from the balloon at 450 cubic centimeters per second. Okay? Now, when the balloon, of course, is releasing air as a sphere, it should be shrinking like this. And as it flows out, we're going to freeze time right when the radius of the entire sphere is 7 centimeters. And once we do that, they want us to calculate what is the rate of change of the radius at that very moment. Okay? So obviously we're talking about the capacity of the balloon versus its size. The capacity of the balloon is going to be measured in volume, and obviously that's in cubic centimeters. The radius, of course, being the size of the balloon, is also going to be measured in centimeters. Then I have this relationship. The volume is 4/3 pi times the radius cubed. That is the formula for the volume of a sphere. Okay, and again, we're making a few assumptions that the balloon is going to uniformly decrease in size, and that when it's blown up, it doesn't deform in any sort of way. But you get the idea, right? So I've got this balloon that's going to shrink, and then we're going to freeze time when the radius is exactly 7 centimeters. Okay? Now, what we need is a relationship between the rates. So I've got my formula here, and I'm going to apply a derivative with respect to t to both sides. All right, so then at this moment right here, dv dt is what I get. And that's going to be equal to 4/3 and pi are all constant, so I'm just going to carry those out. Then it's going to be times 3r squared times dr dt. And then, of course, the divided by 3 and the times 3 here eliminate. So I have dv dt is equal to 4 pi r squared times dr dt. Let's see if we have enough information. I've froze time for a moment to the spot where the radius is 7 centimeters. So I can plug a number in for radius. Okay? And we're given that the air flowing from the balloon at 450 cubic centimeters per second. So I have a rate. Which rate is it? Is it dv dt or dr dt? Well, it's measuring in volume, right? And it should be. The air capacity flowing out, right, is measured in the amount of volume changing. I'm losing volume as the air flows out. Okay? Again, be careful with your rates. It's being released and it's flowing out. I'm losing air. So I can use this as my dv dt, but it needs to be negative. Okay, so let's set up what we've got here. I'm going to have negative 450 so negative 450 cubic centimeters per second is equal to 4 times pi times the radius is 7 squared times dr dt. And I want to solve for dr dt, right? Okay. So that's negative 450 divided by 4 pi times 49. Right? I went ahead and squared that one out. dr dt. 4 times 49 is going to be 196. So let's just be more concise there. 196 pi there. Okay. So let's see what we get. 450 divided by 196 pi. Okay. So we're getting that dr dt is approximately equal to negative 0.731 centimeters per second. And how do I know it's per second? Because the other one was measured per second, right? What happened was the 450 carried units of cubic centimeters per second, and I divided by centimeters squared, right? Square centimeters when I divided by the radius squared. So I lost 2 of my centimeter dimensions, which left me with 1 centimeters, and the per second is still there. So I have centimeters per second is the correct unit, and this is the approximate value of that. All right. Okay, next example. Let's try something a little bit different here. What we have is a plane flies overhead, and a person with the right surveying equipment is watching the plane fly away, and he can see the angle of elevation from the ground up to his straight view of the plane. Okay? And so as the plane is flying away, the angle to the plane is going to go down slightly as the plane flies away, right? Okay, so what happens is if you freeze frame at the moment when it's 64 degrees above the angle of inclination there, okay, he measures that the angle is decreasing, dropping at 3 degrees per second. Okay. Also, he happens to know or be able to guesstimate that the plane's about 9,000 feet off of the ground, right? Maybe he knows something about flight regulations or who knows. And the plane's going to stay flying 9,000 feet parallel with the Earth the whole way. This is the situation set up right here. He's measuring the angle. The plane is already well past, and it's 9,000 feet off the ground. Okay, so this distance x right here is how far away the plane is, and the rate at which this x is increasing should be an approximation of how fast the plane is moving forward, right? An approximation because it's not in the same, plane, but it is in the same, this kind of plane, right? Pun intended the whole way. All right, so what kind of relationship does this angle of inclination have with the 9,000 and the x? Well, let's throw in some trig, right? Let's say that we have the tangent of theta is equal to 9,000 divided by x, right? That's what tangent is, opposite over adjacent there. Okay, well, this is my relationship between the angle and the distance x. Let's measure, let's get a related rates equation now. What I'm going to do is take a derivative with respect to t of both sides. And on this right-hand side, by the way, I'm going to just rewrite it as 9,000 x to the negative 1 so that it makes our derivatives easier to see. We want to be able to use the power rule there. All right, so derivative of tangent theta is secant squared theta times d theta dt, like so. And that's going to be equal to, I'm going to have negative 9,000 because I'm going to bring down the negative 1. And that's going to be times x to the negative 2. But what is that really? That's really x squared in the denominator, right? Because it'll be x to the negative 2 once I subtract 1. But I'm just going to go ahead and bounce it back down. Times dx dt. Okay. So now at this point, I need to look at the equation I've got and decide what kind of information I have and what I want to do from here with the pieces that are necessary, right? So if I'm looking for how fast the plane is traveling, I'm looking for dx dt. All right. I have d theta dt. It's 3 degrees per second. Wait a second. Double check your rates here. The units, I mean. The 9,000 is measured in feet. The x squared is feet squared. So I've got 1 over feet, basically. Right? Secant is unitless because it's a trig calculation of ratios. And then d theta dt right now we're trying to say is in degrees per second. Well, that's not what should be happening. Over here, since I have 1 over feet, feet over feet squared is just 1 over feet. This is in feet per second. If you put all this together, I just have per second, units per second, the unitless units per second. Whereas over here, I've got degrees per second. Something's not right, okay? And in fact, that's true. Something I probably said way back, and I'm going to remind you of now. Degrees does not have a direct connection with the world. Degrees is a weird made-up unit by early man just to make angles easy to understand. What we need are radians. You can use degrees all you want with the angle inside of the trig function, because that doesn't matter which format it's in. Trig, once you do the sine, cosine, tangent, whatever of the angle, it's going to give you whatever ratio. But this rate needs to be properly measured in the proper units. Radians are unitless. They're a relationship to the world through ratios. Okay? So that's exactly what we need. We need to have something that relates to the world that is unitless per second, because that's the kind of measurement I'm getting on this side. Okay? Or let's look at it another way. If I want to solve for dx dt, right? I want to solve for this. I'm going to multiply the reciprocal of this to the other side. So I have negative x squared over 9,000 times secant squared times d theta dt is equal to dx dt. Okay, so again, this is feet squared, and the 9,000 is feet also. So altogether, that's feet. No units, and hopefully just the per second, because this needs to be feet per second. That's what x is being measured in, feet right here, right? So in other words, the theta right here cannot carry any degrees with it. In order to have just the per second here, units per second, this piece right here needs to be measured in radians. Okay? Radians just gives you a portion of something. All right, so to make this even easier to plug in the calculator, I'm going to take the route of replacement. What does that mean? Well, okay, so look at what you have. I have an angle, and I have d theta dt, right? I don't have an x anywhere in that freeze frame, right? We froze it at 64 degrees. And remember, in one of the earlier problems, what we did with the x and the y was we just found the other values to plug in. Fine, you could do that. You could actually solve for x here, right? From this statement right here, I could say that x is equal to 9,000 divided by tangent theta. And then I could plug in the value of theta that's useful to me. And then I'll have something that I can crunch for x, but it's going to be a crazy decimal. I'm going to have to chop it. And then I'll take that and plug it in and then have to chop again. For approximation's sake, I think what I'd rather do is, instead of plugging in the value of theta, I can actually use this statement to replace x here. And then just make my formula easier to plug in, because then everything will be in terms of theta. Okay, so let's do that. I'm going to have negative 1 over 9,000. That's right here. I'm going to have this squared times secant squared times d theta dt. Okay, now I'm just going to add, I'm doing this as an extra step just to make it easier to plug in the calculator. But if you prefer just computing what x is and then plugging it in and then hashing it out, you could totally do that from here. Okay, I'm just going the extra step to make it a little cleaner. All right, so notice this. One of these 9,000s is going to wipe out with, this is squared here, so it's 9,000 squared and tangent squared. The 9,000 is going to wipe out one of those 9,000s. Okay? So next, what I've got is negative 9,000. And then I've got secant divided by tangent. Okay? Since they're both squared, I'm just going to say secant theta divided by tangent theta, and I'm going to simplify that. I'm going to simplify it over on the side over here, just to keep it separate. Secant times 1 over tangent. 1 over tangent. I'll do the squared times secant squared. Right? Okay. Well, 1 over tangent squared is going to be cosine squared over sine squared. Think about that for a second. Tangent is sine over cosine, but I'm doing the reciprocal. So it's cosine over sine, and they're both squared. Secant is 1 over cosine, so 1 over cosine squared. Notice these are going to go away, and it leaves me with 1 over sine squared, which is equal to cosecant squared. Okay? So this piece right here simplifies into cosecant squared theta times d theta dt is equal to dx dt. So for just a little bit extra of the step there, well, maybe 1.5, 2 steps, I now have something that's all consolidated into the type of information that I have. Okay, so that's another way you can go. You can use some substitutions while you're in your rate relationship there to try and clean it up a little bit. In this case, it wasn't too far-fetched. Okay, so now what we have left to do is to just plug in the values. God. Somebody already complained about the test grade. So let's plug in those values, right? In the calculator, what I'm going to do is I'm going to do negative 9,000 divided by, since it's cosecant, I'm going to divide it by sine of 64 squared, and the 64 is going to be in degrees, right? Although I can't type the degrees in the calculator, it just needs to be in that mode. And then times d theta dt. Now be careful. That's negative 3 degrees per second, right? So the negative is because the angle is dropping, and it's in degrees per second, but remember we can't do that, it has to be in radians. So I'm going to say times pi over 180 to convert it into radians per second. All right, so now let's crunch this. We've got double negative, right? So that's positive, and it should be, right? Because it should be gaining distance away. I'll say 9,000 times 3 times pi, right? Divided by 180. And then I'm going to divide by sine of 64. Make sure to use the parentheses appropriately, squared. Like that. So I'm getting 583.338. So dx dt is approximately 583.334, and that's in feet per second, right? So what would it be in miles per hour, let's say, right? Let's convert that into miles per hour. So I would take the answer that we got, right? The answer, and I'm going to convert from seconds into hours. So I'll say times 3,600, right? Times 3,600. And then I'm going to divide by 5,280. And that's because there's that many feet in a mile. So I'm getting 397, right? 397 397, let's just say 398 miles per hour. Okay, and of course either one of those is fine. It just depends on how the person asking the question wants the answer, right? I just thought I'd throw a little spin on that there so we could see how it relates, right? Pun intended. Let's have a little more fun. Here I have two boats sailing both towards a port, okay? Boat A is traveling at 50 miles an hour, and from the port, it measures the bearing of the boat to be north 40 degrees west from the port, right? Of the port, so that's this right here. North, and then 40 degrees in the western direction is the bearing out to the boat, okay? And it's traveling whatever the boat's equivalent of 50 miles per hour, right? Boat B can travel and is traveling 45 miles per hour, and from the port, his bearing is south 67 degrees west. So that's south, right? And then 67 degrees into the western direction out to boat B. So then what we're interested in is how fast is the distance, I've labeled it as L, between the two boats themselves. How fast is it changing, right? What's the rate of change of this distance right here, L, as both boats A and B are approaching the port? So as they get closer to the port, right, their distance is going to shrink between them, right? They're going to get closer and closer together. And what we want to know is how fast is it changing at the freeze frame moment when boat A is 20 miles out and boat B is 30 miles out, all right? So whatever else is going on, the one moment in time they freeze, boat A happens to be 20 miles away, boat B is 30 miles away from the port in those respective directions. So we're saying that they're both sailing straight in, they're not going to turn, the angle is never going to change in any way, shape, or form, okay? So we're assuming no big tidal waves knock them out the way or anything like that, or they don't have to change their bearing. They had the perfect bearing and stayed going straight the whole time, okay? So what I've got here is a triangle that is formed using the bearings and the length between boats A and B. And it's not a right triangle. As you can see, the angle between north and south lines here should be a total of 180 degrees. And so if I add the 40 and the 67 degree angles here, that's a total of 107 degrees. And therefore, there should be another 73 degrees left over in between those two, right? So this angle right here should measure 73 degrees between the two boats, between the two bearings from the port out to the boats, okay? So at the frozen moment, right, I've got one side is 20, one side is 30, the other side I don't know, and I've got the angle between the two bearings, which is opposite that length. It's not a right triangle, so I can't just do Pythagorean, but we do have another way of relating them, right? I have the law of cosines, okay? So let's jot that down. If I label this side right here, the distance to A, I'll label that one with the capital A, and then the length of this side I'll label with the capital B. According to the law of cosines, let me just shrink this up a little bit, L squared should be equal to A squared plus B squared minus 2AB cosine of 73 degrees, right? So notice I didn't put theta or an L angle or whatever, because we're going with the assumption that the boats are never going to get turned or drifted or anything like that, and that this angle is going to stay as both boats come into port, which is a slight approximation because of the curvature in the earth and the waves and everything else, but we're not going that complicated, right? So I've got a relationship now between the distances of the two boats and the length between them. All right, so now I need a related rates statement. So I'll be taking the derivative with respect to t. If I do d over dt of everything, right, then L squared becomes 2L dl dt. Same thing with the a squared and the b squared, right? I'll have 2a times dA dt plus 2b times dB dt, right? And now I get to this next bit. I want you to notice that this is a times b, and both of those are considered to be functions of the t that I'm taking the derivative of. The 2 and the cosine 73 are constant. So I've got minus 2 cosine of 73 degrees times, and then the a times b is going to be a product rule. So I'm going to have a times dB dt plus b times dA dt, right? The product rule says I would take derivative of b while leaving a alone, plus take derivative of b while leaving a alone. Or did I say derivative of a leaving b alone plus derivative of b leaving a alone, right? Product rule. Yes. So that's what I have here for this. Notice I have multiplications of 2 through every grouping. So I can go ahead and divide everything by 2 and make that a little bit easier on myself, right? Divide by 2. Okay. At some point, remember what I'm interested in is the rate at which this length is changing. That's going to be dl dt. That means I'm going to need to divide by L after I do all of these other calculations. Well, let's see. Do I have enough information? At the frozen moment that we're in, 20 should be equal to the capital A, right? Because we said that length right there. So that's what we're saying right here. This is going to be capital A. This right here is going to be capital B. And then what about dA dt and dB dt? They're speeds, right? So I'll have to say negative, right? Because the length is decreasing as it gets closer to the port. I'll have to say negative 50 miles per hour is dA dt, and negative 45 miles per hour is dB dt, right? So I've got all that information. It seems like the only thing I'm missing is the capital L that I'll need to plug in. I know in the last problem we did a substitution that sort of got rid of the extra info part of it. This one's a bit too, complicated for that. It's got too many moving parts. I'm just going to find the missing value of L for this frozen piece of time, and then I'm going to, plug everything back in. Let's start by getting some of the early parts out of the way, though, right? So far, what I have is L times dL dt is equal to, and then I'm going to do all of these pieces here. I've got A, which is 20, times dA dt, which is negative 50, plus B, which is 30, times dB dt, which is negative 45, minus cosine of 73 degrees times A times dB dt, so that's 20 times negative 45, plus B times dA dt, so that's 30 times negative 50. Okay? Be careful of your signs here, right? We had to put the negatives into the rates. Now I've got L times dL dt is equal to, I'm going to add these up because I can. They're all outside with like terms and everything. So that's negative 1,000 and negative 1350. So negative 2350. Now right here, see this negative? I'm going to be able to get a negative factored out here. This is going to end up being plus. 900 and 1500 is 2400 cosine of 73 degrees. Okay. All right, so we've gotten that side reduced down. I'm going to divide by L, right? To solve for dl dt. I'm going to divide by L here. I need to know the value of L for this frozen piece of time. Okay? Well, that's not a big deal. I can still use the original law of cosines to figure out a value of L. So let's do that real quick. I have L squared is going to be equal to 20 squared plus 30 squared minus 2 times 20 times 30 times cosine of 73 degrees. Alrighty. So L squared is going to be equal to 400 plus 900, right? 1300. Then I've got a minus 2 times 20 times 30 is 1200, right? Because 4 times 3 is 12, but 2 zeros. And cosine of 73 degrees. So really, L is going to be the square root of 1300 minus 1200 cosine 73 degrees. Right? So I'll take that value and plug it in for L. Okay? So now it's time to do some crunching. Right. So then dl dt is equal to, well, let's say approximately, right? From this top calculation here, I've got negative 53.8, no, 0.5 ish. And then, oh, no, wait. Blah, 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 blah. From this top portion, I've got negative 1648.307.909 divided by the 30.808-ish. So dl dt is approximately negative 53.5. And let's double check all our units because the other two rates were in miles per hour, right? This should also be in miles per hour. It does make sense that it's negative, by the way, right? Because as they get closer, the distance between them should be shrinking. Let's check our units, right? So I've got a distance times distance over time, distance over time, and then distance over time for those three. And then I'm dividing by distance, right? So if I divide by a distance, it'll take away the extra units of distance from each one, and I'm left with distance over time. Yes, so miles per hour for each one. Absolutely. Let's finish up with another oldie but goodie traditional problem that people love to ask when we're talking about related rates. And that is the good old triangular trough, water being drained out of the trough, right? So I've got this trough, which is the shape of a triangular prism. And don't forget, what a prism is, means that you just have some shape that's just an extruded version of whatever the end side panel is, right? So every cross section along the prism, is the exact same shape. That's what a prism is. Okay? So then, since we're talking about volume, just a quick refresher, the volume of a prism is the area of one of those cross sections just times the length, right? Because it's the same cross section all the way along. You're just multiplying how many of those cross sections you have, and it makes up the total area. Okay? So the trough contains water, and the water is being drained. So it has a spigot on one end, right? And maybe it's a big vacuum hose or whatever, right? The water's being drained out equally from the bottom to make sure it's all level. Okay? And the trough is level. It's not tipped in any sort of way to make the water do weird things. That's another problem for another day. Okay? So it's asking, how fast is the height of the water sinking down if the water's flowing out at 1/2 of a cubic foot, 1/2 cubic feet per second? Okay? When the water level is at 2 feet from the bottom point of the trough there. Okay? So the thing you have to realize is the height is not going to have a linear relationship with the volume because of the way the triangle is shaped. If it had been, a rectangular prism, then the height would have a bit more steady of a relationship with the volume because each of the slices would be the same. But the way the water is slicing in the triangle, every time it goes down, the triangle that the water is using as its own prism, right? Because think about it, the water filling up the trough would have its own prism shape that would be slightly smaller but proportional to the full volume of the entire trough, right? The water itself filling up only a small portion at the bottom, but still having the same depth, would also be a triangular prism, just a smaller triangular prism, right? Okay, so the water's flowing out, and as the height goes down, the rate at which the height is changing is going to be different at each moment because the actual amount of water related to the height is decreasing. Okay, so it's not a linear relationship there is the point. So let's figure out how to compute this volume first, right? We've got that the volume is the cross-sectional area times the length, and our cross-section is a triangle, which, as it always has, a triangle, the area of a triangle is 1/2 the triangle's base times the height, right? If you're talking about the full trough, like if it was all the way up to the top, the height would be the 3 feet, right? And the base would be the 4 foot all the way across. So then the volume of the entire prism would be 1/2 times 4 times 3 times 10. Okay? That would be the volume filled to the maximum. But that's not where we're at. And I need a relationship that probably would be more productive if it was directly from V just to H, since that's the relationship I want to focus on. Okay? We're going to use symmetry to our advantage. Here's a cross section of the trough right here, just one of the slices in the middle or on the end or whatever. The maximum height is 3 and the total width is 4, but notice the 3 height piece is actually a bisector since this is an isosceles triangle, right? The altitude also bisects this thing into 2 right triangles, okay? Since this is a right angle with the height and the top of the triangle, if I were to slice somewhere lower, like let's say the water level was here where I'm slicing, that would still be at a right angle with the height, okay? Because it's keeping parallel with the top line, right? So what I'm doing is I'm just going to say it's at some height, nothing yet. I'm not going to pick the 2 feet yet. Just if the water is at some height, okay? And that means the sides have shrunken in a little bit. I'll just label the length from the center to the edge R, okay? Since this is a bisector, and given the way that this is parallel to this, what I actually have is 2 similar triangles. And remember what similar means. If I do ratios of sides, those 2 ratios have to be equal. Similar triangles have proportional side lengths. Okay, so what does that mean? It means if I were to look at 2 versus 3 in the big right triangle here, you see the big right triangle here, right? I've got a right triangle like this, where this is 2 and this is 3, this is a right angle and this is some other angle, right? Then I've got a smaller triangle just nested inside of it, where this angle and this angle have to be the same because they're shared, and this would be R and this would be H, right? So this triangle is just inside of that one, and it makes them similar because of the way these 2 are parallel. Okay, so what does that mean? Well, what it means is I could set up a proportion that says 2 versus 3 should equal R versus H. And then you're thinking to yourself, well, what's this R business anyway, right? What does that even matter? Well, here's where it matters. Look. Because those were similar triangles, I was actually able to get a relationship between R and H. R is just a dummy variable right now. I'm just using it to label a certain length there. But I need that length to do the area of the smaller triangle here, you see, because I need the length, the base, times the height. Okay? So the R is representing part of the base of the smaller triangle where the water height actually is at. So if I can replace R with some sort of H calculation, then I could have everything in terms of H. And turns out I can. Look, multiply both sides by H here, and what we have is 2/3 H is equal to R. Okay? So this piece right here, where R is actually just 2/3 of H at every height. So as the H height goes down, right, the base shrinks as well, and this piece of that will always be 2/3 of it. Well, the whole base then would be how big? For the whole base, right, if 1/2 of it is 2/3, then the whole base from here to here would have to be a total of 4/3 H. And that's now what I can use for the smaller cross section of where the water actually is, not the cross section of the whole bin, because the water's not at the max level. But if I know some H height now, I can calculate the area just with that H, because I can do 1/2 of the base times the height for this triangle. So here's the relationship. The volume of the water, not the volume of the trough itself, the volume of the water at some given height is going to be 1/2 the base times the height times the depth, right? That's this calculation right here. Okay, so I was able to get that where at some lower level, right, the actual base is 4/3 of the height. I can simplify this. My volume is 20 over 3 times H squared, right? I now have a relationship between the height of the water and the volume of the water in the tank. Okay, now remember, this V is the volume of the water, okay, not the volume of the whole tank. The tank is not changing size at all. The water is. Now do your derivative to get the related rates portion. That means that dv over dt, right, the derivative of v, is going to be equal to 20 thirds times 2h times dh dt. Right? Chain rule there, right? Doing my normal chain rule derivative because of the implicit differentiation there. Right? Okay, so this we can figure out. It says that the water is flowing out at 0.5 cubic feet per second. That's dv dt. Flowing out means it's negative, right? And this is the number portion of it, per second. Okay? They want to know how is the height changing when the actual water level is at 2 feet. So that's my height is going to be the 2 feet. Okay? So let's plug in some actual values here. My dv dt is 0.5, negative 0.5, and it's equal to, I have 20 over 3 times 2 times 2, right? So that's 4 times 20 basically, 80 over 3 times dh dt, right? Okay, so I'm just going to multiply by the reciprocal here. I've got negative 0.5 times 3 over 80 is equal to dh dt. So then, since this is 1/2, I could write the fraction as negative 3 over 160 is equal to dh dt. And you can get the decimal for that, but I mean, it doesn't really matter. Check your units, right? The dh dt should be measured in feet per second, right? The 0.5 was in cubic feet. And then the 80 over 3 had the height measurement, and then it also had the other height measurement inside of the 20 over 3, right? Because here's 2 of your heights, but then the 10 also had one of the height measurements in it. So one of your height measurements is here in the 20 over 3, right? Times this height measurement means I'm dividing away 2 of my height units. There were 3 total. It was cubic feet. So that means there's a foot left after doing that division. So it's feet per second left over, just like the units of dh dt should be. All right? So there's my units of measure right there. Let's go ahead and punch it up real quick. Negative 3 over 160. Or let's do it the other way. Let's do 0.5 times 3 divided by 80, right? So then I'm losing 0.01875 feet per second, right? And of course, at that point, it's kind of hard to see that small of a measurement of a foot. That's when we would start converting it into like inches per second and things like that. So let's see, times 12, right? 0.225 inches per second lost, right? Might be a little bit easier to see a 1/4 of an inch loss rather than that measurement of feet. But anyway, I hope these example problems have helped you see how related rates is really just an application of formulas. You need to find a formula that fits your relationship, and then you can take an implicit derivative of that formula and then plug in your rates and values as needed.